Hello friends, welcome to this video. In this video, we will delve into the fascinating world of generative adversarial networks and specifically explore the implementation of conditional DCGAN. Conditional DCGAN is an extension of traditional DCGAN architecture where the generator not only learns to create realistic images but does so under specific conditions. These conditions could be anything from class labels to additional input data that guides the generation process. In simpler terms, it allows us to control and influence the generated output based on specific criteria. We will start by taking a look at the dataset first. So the name of the dataset is male versus female, and it's a classification dataset that I have downloaded from the Kaggle website. And it has two classes, that is female and male, and they both contain human faces, and the female class contain 492 items and the male class contain 476 items. So this is a small data set, but for this demonstration we're going to use this. So here are the few samples, and all the samples are resized to 256 by 256 pixels. So you need not to resize it or pre-process it. You can directly use this size, or you can decrease the size accordingly. And here are the few samples from the male faces. So we are going to use this data set for our conditional DCGAN. Now we'll start with the coding part. So first of all, we are going to import all the required libraries and functionality which we require. And here you can see we are using TensorFlow framework for our implementation. And there are other libraries which would help us to implement some helper functions. Next, we're going to specify some constants or some value. So first is the image height, image width. So we are going to resize this image to 128 by 128 pixels. After that, we have the number of channels in the image, and then we specify the stride value. So this stride value would be basically used in the while building generator and the discriminator. Next, we're going to create a function called create_dir, and this function would take a path and it would check if that path exists or not. If that path does not exist, then it's going to create that path, or simply it is used to create a folder. Next, we have another function called load images, and this function basically reads the image and pre-process them before we pass it to the training pipeline. So this load_image functions take the image path and its respective label. So first of all, we read this image, then we decode this image. After that, we resize it accordingly. So here we're going to resize it from 256 by 256 to 128 by 128. After that, we're going to change its data type to float 32. Next, we're going to normalize its pixel value to -1 to +1. So initially the range of these pixels are 0 to 255, and we normalize it to -1 to +1. So this is the range, and after that we give the normalized image and the label back. So this label would be an integer value, that is 0 or 1, because we have two classes here in our data set, that is female and male. Next, we're going to build our training pipeline function. So this function, this tf_dataset function would help us to build the training pipeline. So it take list of images path, and then list of label, and then a specified batch size. So here we use tf.data API, and from there we have from tensor slice, this is a function, and we give it a tuple, and this tuple contain images path, it's a list, and then the labels for these respective images, and this is also a list. After that, we shuffle this data set, and here we use our load image data set to pre-process our image. Basically, we do not pre-process a label here because it is not required. After that, we create batches, and each batch contains specified number of images. After that, we have this prefetch function. So what this prefetch function does is it make sure that some of the batches are already in queue while one of them is in the training process, so that training pipeline is optimized. Now we'll move on to our core functionality, that is building the conditional DCGAN. So first of all, we will have our convolutional block. So this convolutional block basically contain a convolution layer, then a leaky ReLU activation function and a dropout. So we'll start with the name of the function, that is conv_block. It take the input feature map, then the number of filter. So number of filter basically means number of output feature channels. Then we specify the kernel size, then padding. After that we have a stride value, and after that we have activation whose default value is true. So this means if this activation is true, we're going to apply leaky ReLU and the dropout. So this conv block starts with a convolution layer, and we specify all the parameters in it. And here you can see we do not use bias. And here we have a kernel initializer. So just make sure you properly initialize the kernel with the random normal initializer with mean 0 and standard deviation of 0.02. Okay. After that, the output of this conv block would pass to the ReLU activation function and drop out if the activation is true. If not, then the output of the convolution layer would act as the output of this function. So this is all about this convolution block. Next we have our decon block. So again same thing, we have name of the function, that is decon block, and it is mostly would be used in the generator neural network, and it take your input feature map, number of filter, kernel size, padding, and a stride with the default value of 4. So our first layer is conv 2D transpose. So what this layer does, it take an input feature map and it increases or upsample it to a specified size. Let's say here we specify stride of 2. So if your input feature map is of size, let's say 128 by 128, and we give it to this conv 2D transpose layer, and the stride value is 2. So from 128 to 128, it would become 256 by 256. And this layer basically learns how to upsample those. So it is different from normal bisampling, bilinear upsampling layer, which we sometimes use in some of our videos. So this layer basically learns. After that, it is followed by the base normalization and the leaky ReLU. And here in the conv 2D transpose, you can again see we set use bias to false, and we have initialized the kernel with the random normal, mean 0 and standard deviation of 0.02. So these are the two blocks which we're going to use for the implementation of our generator neural network and the discriminator neural network. Now let us start building our this generator neural network. So let's go to the start. So here we have our function name, that is build_generator, and we first give it the latent dimension, then embedding dimension, and then the number of classes which we have in our dataset. And here the value is 2, male and female. So this generator would take two inputs, that is the noise and the label. So label is basically the condition, is the criteria which would help it to generate specific kind of images, and it's going to give you the fake image. Okay, so these are the input and the output. Now let's dive into its layers. So first of all, we define noise. So this would be the input. After that, we have a dense layer, and here you can see in the dense layer we have image height divided by the stride, and if you see, we have specified the stride value at the starting, that is 32. Then we have image width divided with the stride. So stride basically defines that we need to we're gonna have a smaller, we're gonna like small the size of the image. So this generation process would begin with some specific size. So this is defined by this image height divided by stride and image width divided by stride, and then we multiply this with 256. So these specify the number of feature in the dense layer. So if we divide this 128 by the stride, that is 32, it became 4. So here the features would be 4 into 4 into 256, and that became 4 into 4 16, and 16 into 256 would become 4096. After that it is followed by a Bayes normalization, a leaky ReLU, and now you can see we are reshaping it to a spatial feature map which has height, width, and the number of feature. So this is about the noise and its layer. Next we have the label. So here label would be only a single value, that is 0 or 1. So this specifies the size of the label input. After that it is followed by the embedding layer. Next we have a dense layer. Again you can see the same size, same number of feature map in that label dense layer also, followed by the Bayes normalization and the leaky ReLU activation function. After that we again reshape it. Now we have feature map from both the noise and the label. Here we concatenate both these feature map and we get a joint representation of both the noise and the label. Now it is followed by 5 set of deconvolutional block where we upsample these feature map. So let's say here it became 4 by 4. So the output of first decon layer would become 8 by 8, then 16 by 16, then 32 by 32, then 64 by 64, and at last in the fifth decon block the size of the feature map would be same as we specified in our height and width, that is 128 by 128. After that it is followed by a convolution block where we have number of filters as equals to number of channels in our image. And at last we have our 10H activation function which would generate our fake image and we get our model. So this is about the generator neural network. Next we have our discriminator neural network. So this discriminator neural network would take an image and the label and would predict whether this is a real image or a fake image, and that is the task of the discriminator. So this build underscore discriminator function take embedding dimension and the number of classes, and it take two things as the input. First is the image, and this can be fake or real, and second is the label, and at last it's going to give you a prediction, that is a probability whether it is real or fake. So first of all we have our image, and then we have our label. So we pass the label via the embedding layer. After that it is followed by the dense layer, and in the dense layer we have its feature equal to image height multiplied by image width 1. Okay, then it is followed by the Bayes normalization and the leaky ReLU. So why do we do this image height, image width? Why not anything? Because see, this image has specific dimension of this image height, image width, and number of channel, and then this label would go to the embedding, then go to the dense layer. So this dense layer, after that it's followed by Bayes normalization, leaky ReLU, and then reshaped. So it is, the features are given in such a way that we can easily reshape them, okay, and then concatenate with the input, because concatenation also requires specific dimension. Specific features can only be concatenated, not any feature. You cannot concatenate two feature. You can only concatenate if their dimension are same. Here we are concatenating them on the last dimension, so it can change, but rest of the two dimension need to be same. That is why we have specified these as the features in the dense layer. After that we concatenate both the features, that is image and its label. After that we have 5 set of convolution layer, and in each convolution layer, we increase the number of filters and the stride became 2. So stride of 2 means the output would be half. That is, if the size here is 128 by 128, we give this 128 by 128 feature as the input to this con block. Instead of 2, it would become 64 by 64, and same goes, and at last we flatten the feature map and we have a dense layer with number of feature as 1, because it's a simple binary classification, real or fake, and we get our model. Now we will move on to the train step function, and this function basically defines all the operation that happen within an epoch. Okay, so this function would take real images, real labels, latent dimensions, number of classes, generator and discriminator neural network, and their respective optimizers. So in deep learning, in training, we train basically on batch of images, and batch basically refers to in the number of images. So the number of images within a batch is defined by the batch size. So if we first have the value of batch size, after that we define the loss, and for the loss we are using binary cross entropy, where we set from log x equals to true and label smoothing equals to 0.1. So now we'll start with the training process of discriminator. So first of all, we have a random noise as the input for our generator. Here you can see we are using a loop. This means we are training discriminator more than the generator. So what is the reason for this? So the reason is that we want the discriminator to be stronger than the generator, because a stronger discriminator can force the generator to generate more realistic images as it can easily distinguish between the real and the fake images. So this would force the generator to fool the discriminator, and that would increase its ability to generate more realistic images. Now let's go inside the training part. So first of all, we generate fake images, okay, and for that we give noise and the real label to the generator neural network. Now we have both fake image and the real image, so we give both of them to our discriminator so that it can distinguish which is real image and which is fake image. Okay, so we give real image and real label, and we get real output or the prediction. Then we give fake image or generated image and real label to the discriminator. Next we calculate loss, and for loss we need ground truth. So we have our real output and fake output. So for real output the value would be 1, okay, for its ground truth, and for fake output it would be 0. So here we have a function called tf.once underscore like, and it take the real output. Okay, so what it does, it create a tensor with same dimension as the real output but with values as 1, and same goes with the tf.zeros like. It would also take fake output as the tensor and create another tensor of same dimension with 0 at its all the value inside. Now we got real loss and the fake loss, and we add both of them and we get our discriminator loss. Then we calculate the gradient and we apply those gradients. Now we'll train the generator. So for generator, again we generate fake images and we give noise and real labels. Okay, after that we give these fake images and real label to the discriminator and we get the fake output. Now we would calculate the loss. So we give fake output to the loss function, and now we need to give ground truth to it. So now our ground truth for the fake image is generated. So here the generator need to fool the discriminator. So this means the generator should feel like these are real images, and to feel them that they are real images, the ground truth should be 1. So here you can see in the loss function it uses tf.once like fake output. Same as above, its functionality is same as like here, just that here in the generator part we use fake output and we give 1 as its value. So we are forcing that this is real output, not the fake one. Then we calculate the gradient using the loss function. We apply those gradient to our parameters. Next, we have a function which would help us to save the generated sample during training. Okay, so it takes these examples, that is predicted samples, that is which epoch, and n. Basically it's going to create a square image, that is n as the number of row and n as the number of column. Here n is an integer. Then we have example, we again pre-process them and make sure it's all the pixel value are again back to the range of RGB, that is 0 to 255. Then we have the name of the file and this whole operation to save the image. And at last here you can see we are changing it from BGR to RGB. And this thing I realized in this video only, because in previous videos I'm not doing this. Okay, now we'll start with the training process. So first of all, we'll define our main function. Okay, so these are all our hyperparameters. So we have a batch size of 128, latent dimension 128. So you can increase or decrease the batch size according to a GPU memory. Okay, then we have embedding the dimension also as 128, number of classes 2, number of epoch 1000, and number of sample 100. Okay, then we have path to the dataset, and let me change it, that is male versus female. So n sample 100 is basically gonna create images equals to 10 into 10. I hope you got it now. These n samples, we're gonna give this n value here. Okay, and so that would be 10. Okay, now what we're gonna do, we're gonna get all the images path. For that we're gonna use glob, then specify the path and the inside path we're gonna say star, that is all the folder and all the images with the extension of png. So this way we get all the images. Now let me print number of images or length of this images path list. So let me run the code and check. Okay, I have to change my environment to TensorFlow, not PyTorch. I basically use both the TensorFlow and PyTorch in my research papers. Images path, again a mistake. Mistakes are common part. We basically learn from mistakes. So you can see 968 samples from both male and female. Okay, now we need the image label. So I'm going to explain this part of the code to you. Okay, so what we have this 968 images and we need labels for them, whether the respective image is male or female. So we need specific integer value. So this is empty list. Then we're going to iterate over the images path. So let me write a break here and I'm going to print path. So this is the path and you can see this is male. So how do we extract this male value from here? Okay, so we have our path printed here. So what we gonna do, so before that we need labels. Okay, we need list of labels. Just to be sure, let me copy this part of the code. I forgot to paste it. Okay, so we need labels, that is male and female. Okay, so let me just comment this out now and run this for once so that we all are on the same. Okay, so the number of label 2 and the labels list, male and female. This is the list we require. You can manually do it or you can use my way. What I've done, I have basically list all the folders inside the path, then print the list length and then what is the in the list. So now we going back to our images labels. We have our path Again, we're gonna run it. We have our path, so we need to extract this mail. So what we're gonna do, we're gonna say name is equals to path dot split. I hope you have used a split of a function sometime. So what it does, it break your string based on a specific character. You can see we have used slash and it has converted into a list. And you can see our class name is on second position. Now one thing what I'm gonna do, I'm gonna say -2 here. You can even say 0 and 1, but initial path can change in any of your code. Okay, maybe you have a different path, but it would always be second last from the last if you reverse the list. You can see mail. Now we're going to calculate the index of this name. So we have this label list. That is why I said we need this list, that is male and female. So we have this name, we calculate the index from this list, and we have this index and we append it here. So let me print the index value, and let me remove the break from here. Let's run this part, and you will see 1 1 1 1 1, and sometimes 0 should also be there. You can see 0 0 0. That's how it works. Now let me print how many images and how many labels do we have. Okay, we have 968 images and 968 labels. It is fine. So I would recommend using more images because these are really less images for a GAN. Okay, but still our model work and able to generate some realistic, not too realistic, but at least at that level that you can say that this is working. So we're going to create two folders, that is samples and save model. So in the sample we're gonna save the images which are generated during training, and in save model folder we're gonna save the weight file of both generator and the discriminator. Next we're gonna create generator neural network and the discriminator neural network by specifying value within their function. Next we're gonna call both the neural networks, and we're gonna run and have their summaries. So first we have is the generator. It take class label and then noise as the input, and we get our fake image, that is 128 by 128. And here we take class label and we take image. Where is the image? It should be some this image. Okay, and we get a classifier. Now if you remember, when we are building the generator, I've told you 4 by 4 when 128 divided by stride of 32. So you can analyze these layer later in your system. Let's move forward. Now we'll move on to the training part. So first of all, we'll define the optimizer for both discriminator and the generator with same learning rate and beta 1 value. Next we're gonna have an image data set. Okay, and here we use tf underscore dataset function which uses tf.data API. Then we have this seed, that is random noise, and this would remain fixed during the entire training, so that the images would be generated on same seed, same noise, so that we can compare how the images improve from first to second to third, fourth, fifth epoch, like this. Now we also need seed labels because this is conditional GAN and we need a condition. Here the condition would be label, class label. So this is class label, and here if you see we have 100 specified here, that is it would create a square of 10 by 10. So we have specified 10 labels, that is first 5 would have class 0, next 5 would have class 1. Okay, now we have seed labels. Okay, Okay, now we'll move on to the training part. Okay, so we have a loop here over number of epoch. We start the time. We have two variable to store the value for discriminator loss and the generator loss. We now iterate over the image dataset, which give us batches of image and batch of label, and we give those specific value to our train step, and we get our discriminator batch loss and the generator batch loss. We sum those in the specific variable, and we after the loop of this image dataset is over, we calculate the mean discriminator loss and mean generator loss. We save both the generator neural network and the discriminator neural network, and after that we predict. Okay, we predict using the seed and the seed labels the examples, and we save those. Now we're gonna print how much time it take for it to train and what are the losses. Okay, now we can train it. So it's gonna take some time to train, and I think till that time we can work on the test or prediction file, and the prediction is really easy. First of all, we're gonna import some libraries. Here in the test we require few. After that we have again our same function, that is save plot, just with few changes. After that, let me copy paste code again, because this is really simple code. So we have number of sample, we're going to generate 100 mean a square of 10 by 10, latent dimension, embedding dimension, and these two values should remain same what is specified during training. Then number of classes, again this should remain same. Then we generate our generator neural network. We then have a latent point for the noise, and its size is number of sample by latent dimension. Then we have seed, that is first 5 would be from 0 class, next 5 would be from the first class. So these are 10 point, and how many sample we have? 100. So in this we create 100 of them. So you can see we iterate over our these points, and what we do, we give seed label plus equals to item into square root of number of sample. So we say is 0, it multiply by 10, it became 0 0 0 0 0, then 0 0 0. So it would create a list of 100 index point with 0 and 1. Okay, and half of them, that is 50 point, would be 0 and 50 point would be 1 in the seed label. Then we convert it into array, and we give it to our model, that is latent point and seed label, and we save those samples. This is really easy. Okay, you can see the training has begun. Let me stop it. Okay, so here are the samples, and it's so in the first epoch nothing is there. So let me full screen. Next, slightly we can see something, then again it's improving. Okay, and now here you can see that because we know this is a face data set, so maybe this is our mind trying to find faces. But if we don't know that this data set belong to human faces, then we don't know. But here we can slightly know that this is face, and not all faces are same. Here also some few faces we can see. So okay, so this is the 22nd epoch. So it's working fine, and it's also saving your weight files. So what I'm going to do, I'm going to replace both these files, both these folders, with the one I've trained. So I've just trained those samples on really huge number of epoch, I think 1000 or 500, and it took time. Okay, you can see, let me show you fast. You can see at the end, we can see that first initial 5 rows are female and last 5 are male. These are not really clean, but at least we know that these are females, these are male. So the images which are being generated by the conditional GAN is based on a specific condition. Now what we're gonna do, we're gonna generate a fake image and we're gonna run test.py. Okay, some messages from the TensorFlow, but we don't want them, and we run this and we get our fake sample. I hope these images you can easily distinguish that first 5 are females, next 5 are male. Some of the images are really bad, but some you can say you can recognize that these are female, this is male. So this is the demonstration of a simple conditional generative adversarial neural network. I hope you learned something from this video, and if you enjoyed it and find it informative, please make sure to subscribe the channel, like this video and share it with your friends or on your social media. So thank you. Have a nice day.